download clustering. Is dbScan working? 8 is hierarchical clustering. Or 7 on real data. Anybody got dbScan working on real data?
I got 8 clusters, but most of it is just noise.
I think one thing with clustering to get it to work better, at least from one perspective, is to get more clusters. You know there's MNIST data, right? And there's 10 labels. You ask for 10 clusters, may not correspond properly with the labels. If we ask for 70 clusters, clearly you can hope that there's not a one-to-one correspondence anymore, obviously, but you can hope at least that each cluster is just one label. So be a cluster of ones and another cluster of ones and another cluster of ones and another cluster of ones. That way, at least there's separation between the clusters. So we've done that. I don't want to go back to clustering. We also done PCA, right? So we've done PCA in detail because this is such a basic feature extraction or dimensionality reduction that you have to know what's going on in there. This matrix P, that's PCA of X, it has the property that P times P transpose is the eigenvalues. So it's like, we call it C, or I forgot, C times D times C. This is diagonal, and this is the eigenvectors matrix. And this is the covariance matrix of X. So P is a rotation matrix. And the new X we have after PCA is the old X multiplied with P. Why I'm giving you this recap? Because you're going to have to implement PCA. Okay? You could call PCA in MATLAB or Java or scikit-learn, but you're going to have to implement PCA, which requires you to get the eigenvalue, eigenvectors of the covariance matrix. So you are allowed to use a covariance function. You don't have to compute covariance yourself. You are also allowed to use an eigenvalue, eigenvector function available in all these languages, like in MATLAB, called eigen. It gives me the eigenvectors, eigenvalues of this matrix. I have to get this P, which is, you could use the C alone if you don't want. I explained in class last time that this acts like weights on each eigenvector. Without this, it's an orthonormal matrix. With the weights, is not. In MATLAB, P includes the square roots because this is kind of a P and this is kind of a P transpose. So that each one of them has to include the square root of the eigenvalues. To get PCA rotated, data rotated, which is the same data, rotated and magnified because I'm using the eigenvalues in here, right? So this is how I get the data to rotate to align with the proper axis, that the variances now correspond to the axis, but this is the same dimensionality because n, this is n times d, this is d times d, so I didn't change dimensionality. If I want a different x new in a different dimension, say t, I'll do x times p of all, but only the columns 1 to t. So t is smaller than t. That way, I get only the first t dimensions, PCA dimensions. If I want 1, I just get the first one. So you're going to have to implement PCA. That's why we spent 2 days on it. But there's a lot more to feature extraction and dimensionality reduction that we're going to have to do, although we can do all those items in that level of detail. PCA is something that you have to do the engineering and conceptually when you run PCA later on whatever data set, academic or production. You have to know what PCA does. First rotate the data to align the axis with the variances, and then pick the first so many axes that you want according to those variances. So what else is there? That's going to be part of homework 3. Here's what I can do. I can ignore the PCA rotation, but still go by the biggest variance. So I could say choose T dimensions or features from existing columns, right, with highest variance. I can compute a covariance matrix and ignore everything that's on diagonal. Maybe sort those features by the, where is the variance on the covariance matrix? On the diagonal, right? Pick the top 10 features or T features with the highest variance. Usually variance is better for a feature, right? The more variance I have, the more description I get for the data. Low variance means all the data is represented in a tiny spot, right? So I could, this should not do as good as PCA because it doesn't do the rotation. It just says out of the features that I already have, pick the ones that have the highest variance. And I can still get T of them, right? This T is the same T as in there. 3. I can come up with a score between any feature. So F is a column or feature or dimension in the data. I can come up with a score between feature and labels, some sort of correlation. And then choose top T features by correlation, by score. Would that make sense? For each feature independently, that's important. Independent. I compute a correlation between the feature and the score. A feature is good if it aligns well with the labels, right, for say classification purpose, and maybe no good if it's totally independent with the labels. And then if somebody says I want just top 10 features, I'll pick top 10 by this score. So we're going to look at two kinds of scores. One is mutual information. Between, say, a feature and the labels. So L are the labels. And we're going to do another score, which is chi-squared. That's a very popular measures of this kind of thing, correlation, right? It's related to something like person correlation. There's several scores, but you should know two things about this. How it's used, like in this way, it's not the only use, but it's one of the uses, feature selection. That's what we're concerned with right now. We can put a big title there, feature selection or dimensionality reduction. And you should know, I won't insist on the math on these things, like what's the exact formula for this. I would insist that you know the concept. What is this mutual information trying to capture? The exact formula, even I don't remember it. You ask me right now, what's the mutual information formula? I have to look it up. But I know what it's supposed to measure. Same thing for chi-squared. It's a statistical test. I don't know the formula, but I know the design of it. What's the principle? That's what you should know. What's the purpose of this correlation? And then one thing that we need to do is what do I do if I have no labels? Our purpose here is still unsupervised learning. So while this stuff works well with labels, it measures the features against the labels independently. Well, then if I have no labels, what? I can't, in principle, I wouldn't be able to use these methods if I don't have the column of labels, right? Okay, so that's 3. Part 4. For part 4, we use classification algorithms for feature extraction. Of course, classification is a big deal, and I'm going to take advantage of that to talk a little bit about regression and decision trees. We already talked a little bit about K-nearest neighbor. That's good, but if you don't take the machine learning class, 6140, some of you won't have the chance to take it. I would definitely recommend that class. If I'll be a data science student of any kind, 6140 will be my absolute priority. But just in case you don't take it, I'm going to spend some time talking about decision trees and regression for one day, so you have a little bit of background what those things are. But our use will be, we can get them not just to do classification, but you do feature extraction. So we'll study two things. One is linear regression. We won't study in the detail that 6140 does it. They spend the whole 2 weeks and a half on regression. We'll spend half a lecture. Linear regression, to do feature extraction, I need something to it. Anybody knows what that is? Which kind? Yeah, which is called L1. Right? Lasso is both L1 and L2. The essential one for feature selection is L1. L1, regularization. Regression can spread its coefficients over many, many features, and it can do very, very well. But that's not feature extracted because it still uses all the feature. With L1 regularization, which we're going to talk about maybe next week, maybe after the spring break, we force regression to only use that many features. We say we don't want a lot of coefficients. Most of them will be 0. Do the best you can by only using that many coefficients. But L1 regularization, it's hard, both engineering and the math. So we won't be able to get into that. But with L1, we could do a feature selection. The other stuff we're going to use is a decision tree. Decision tree, most of you may know how it works. It uses a bunch of features to do splits. And the more it advances, the more it does more splits. And the features used to do splitting are the best features at splitting, which happens to be some of the most descriptive features of the data. That's why they use it for splitting. So if you don't know what the decision trees are, you probably didn't understand what I just said. But most of you have seen a decision tree, have seen how it looks like. We won't do any theory on it, but we'll draw some decision trees. And you can call a package, a decision package, to get, say, top words in 20 news groups or something like that. Now, what's the difference between this, essential difference between this and this? They both, at some point internally, correlate a feature with how useful it is to get some classification or some determination for the label, right? The principle here is that a feature is very correlated with the label. That should be a good feature for classification, right? Suppose I have a magic feature that's one-to-one correspondence to the label, right? Suppose I'm trying to classify patients as sick or not sick, and I have one feature, say blood pressure or something, that's perfectly correlated with the disease, right? Whenever blood pressure is more than something, it's sick. Whenever it's lower than something, it's not sick. Both these algorithms should find that feature immediately. This one should say that's a very high score, it's very correlated with the label, and decision trees or regression should identify that feature as being very important because it does classification really well. What's the main difference between those supervised learning algorithms? Those are definitely supervised learning algorithms. And this scoring function, which is kind of naive, if you want. For supervised learning, why nobody uses this? In other words, there's a fundamental difference here. Why is it that this has so much more power at discovering good features than this correlation? Yes?
Those features might be mapping themselves to some different label. Like, for example, it might be a gender, and that, but we won't want that label. Something.
No, that's not it. Yes?
Maybe that is treating each feature as independent and doing it.
That's
as
it.
is.
So what's the problem with this? Both of them should have the same ability to find the first feature, which is the most correlated with the data, say blood pressure. After that, this algorithm may find another feature which is well correlated with the data, but also very correlated with the first one. So I may have blood pressure and something with a heart, I don't know, rhythm. They happen to be very correlated with each other because they, as anatomy, body works in a certain way. Those two things are very correlated. They both correlated to the labels, but those features don't add anything to the other. Like once you have one of them, you don't need the other because they do the same thing. This kind of independent correlation will rank both features very high because they both correlated well with the label. But for classification purposes, they just duplicates of each other. They have the same information. What would we need to measure to know that? Apart from this correlation, how would we know, okay, those features are, just take one of them, don't take both of them. We need a correlation between the two features, right? So sounds like the covariance. It says, okay, they're both good, but they're the same feature, no point getting both. See, these algorithms are designed specifically with that purpose in mind. Any good supervised learning algorithm, either global, this is a global classifier, this is a local classifier. They will not choose a feature that's correlated to an existing one. Regression can do that without L1. But the decision tree will certainly not do that, right? Once it picks the first feature to do a split, say high blood pressure, low blood pressure, it will never pick a feature that's correlated to blood pressure because that feature will be completely useless. After I split the data on blood pressure, if I have a second feature, say heart rhythm, that's correlated to blood pressure, that feature would not do anything for the data that's been already split. Does that make sense? So if I have a tree here, I use a feature 1 here, F1. Once I do the split into say yes and no, I'm using a binary split. A feature 2 that's being used here for the tree to do split of data will have to be somehow independent of F1. Otherwise, by the internal mechanism of the decision tree, this feature will not be selected. So that's a fundamental difference between 3 and 4. In 3, we don't have any correlation between the features. We just pick the top ones, even though they are identical to each other. What else? 5, for images, we're going to do something called hard features. 6, for text, we're going to do something called topic detection or model. It's a very particular, you can call them heuristics, that apply some math and some engineering to get specific features. Like these techniques won't work for text. These techniques won't work for images. And lastly, 7, we want to use a neural network, TensorFlow, for several tasks, including feature extraction, word embedding. I know this might be a little bit weird language for now. Just going to give you an overview of where we are within this module. What is it that we're trying to do? It's going to take us a few weeks to get there, and there's a spring break in the middle. So I'm going to leave you guys with a big homework for the spring break. Because I don't know how many people are going to use the spring break to do it. Some people will use the days after the spring break. The homework won't be due until well after the spring break. There's not 2B, the next homework coming up. So part of this will require some back and forth between you and the TAs in terms of installing TensorFlow and set up TensorFlow. That's a more complex process than running a regression or decision tree. I bet you can find a package or regression running right now, but this is not that easy. You need somebody who runs TensorFlow to babysit you a little bit to be able to run it. So that's our feature dimensionality reduction feature selection chapter. I'm going to talk about some of these things today. So I'm going to start from this one we did. In here, I don't think there's much to talk about this. You take the covariance matrix, which is the same covariance matrix like before. We look on the diagonal, pick the features with the highest variance, right? So whichever, they may be correlated, that's fine. We pick the top T features has variance, that should be pretty clear. How about this? So first of all, I want to talk about something that's pure engineering, and it's going to be up to you to figure out. Anybody can give me an idea what I do if I have no labels? So I can have these methods that work by correlating a feature with the labels. But in unsupervised data, I don't have any labels, so how can I use these methods? So let me do that first, because this is a general problem. It doesn't matter what it does, what the algorithms do. They use labels, so I need something else that's if I don't have labels. So if I have no labels, I'm going to try to fit it here. There are two options, right? One option is use clustering ID as labels. What does that mean? I have no labels, but I can run k-means first, with say k equal 20, and get everybody to have a cluster ID. That's not as good as the labels perhaps, but in terms of feature extraction, might be reasonably good, because I'm going to use these methods now to say data has been grouped in 20 groups IDs, or 10, or how many. There's some advanced k-means that will figure out the right k for you. Like you don't have to, the k-means we did, we set k to what we want. But there's extra k-means that determines the proper k. I can use some cluster ID as labels, right? What else I can do to use one of these methods is to compute instead that score between two features, F1 and F2. So imagine this, I don't have scores between feature and labels, say mutual information or chi-square. All these scores, high means what? So high means correlated, right? So for these scores, high score means correlation. And low score means what? Independence. So imagine I compute those scores, but I don't have labels, so I'm computing the scores between features. It's like covariance, if you like, right? We can add here one of the possible scores be the covariance. They're very related, those things. Now, if I have those scores, how can I select features? I don't have labels. And I would like to get useful features. I mean, describe the data as well as I can. Somebody gives me a target T. I want 20 features or 50 features. What do I do? Once I have the score, so I will start with, maybe start with a set of features of F with the highest variance. Right? So I start with F, the set of features I want. I pick just one. Which one should be my next feature that I pick? You know, I don't have labels, but I have these correlation scores.
The one with low score.
Lowest correlation.
This one.
So I'll do some sort of loop here, right? Loop from t equal 2 to t, right? Because I want t of the total. Do what? Choose the feature FT that minimizes the correlation, the score, the scores are already computed, between FT and all the other features already selected. So that's a little bit of abusive notation. I don't have score between FT and the whole F. I have scores between FT and all the other features. The first time, F contains only the first feature. But second round, F will contain 2 features. So I have to figure out what mean between all the non-selected features and the ones in F means, right? And then loop this T times, right? So this has a name in graphs, this kind of mechanism. Pick the point or the data or the feature that's as far as possible to the ones you already picked. In a graph, there's a certain name for this property. When you say, pick the first point or the first object, then pick the point that is the farthest away from the ones you already have. Anybody knows that name? Furthest, far, it's making a selection. Typically in geometry, I have this problem with say, pick a convex hull. I want to be as far as possible on the edges of the convex hull. Same problem, right? I pick the first point. In there it's random, but then I want to go as far as possible from the ones I have. And I only have pairwise scoring distance computed. So this is a general recipe heuristic for if I want to use one of these methods, but I don't have labels. I can either cook up some labels somehow. The danger with that is, of course, I can run an algorithm that's really inappropriate. I run k-means on a data set that's not appropriate for k-means. I get 20 labels if I ask for 20 clusters, but they're not good. Maybe I should use different clustering algorithms for that. Or I compute the scores, pairwise scores, correlations, whatever score I want, and then I start selecting features with the property that I don't want my next feature to be very correlated with the ones that I already have. So in here, it's either minimum across all features or minimum average correlation, right? I can take the F against everybody, right?
So when you pick up the minimum feature, right, you might pick up the feature which is completely unrelated to the label if
yes.
you have.
Yes.
If you have.
Right. But keep in mind that I don't have labels, so as far as I'm concerned, I don't know the purpose of this data. I don't know the data is used for heart disease or diabetes classification. So in an unsupervised world, my priority, my goal is to obtain a good representation of the data. I don't know what purpose it's used for. So if I only want 10 features out of 780, I'll pick 10 that are as much as little correlated with each other. And most of those strategies use the features out of the data. So these strategies typically don't do a feature transformation. When I say pick the top T, it means pick top T out of the 784 that are there. So if T becomes really large, I'm probably picking most of the features. Let's say T is 400. By the time I pick 400 pixels for those images, I'm probably getting all the pixels that truly matter, right? Most of the pixels in this image, more than half of them are like corners, have no information. So by picking this way, I'm hoping I'm getting some features that are related. One more thing, what we could add here is I want to be uncorrelated, but also I want to have high variance, right? I mean, if a pixel is all constant, it's white for everybody. Even though maybe uncorrelated to some existing features I picked. There's no point picking a feature that's very, very tight in terms of variance. That's usually useless for any purpose.
What if you start merging features that have very high correlations?
You have to know why you do that. I'm not going to dismiss it as you don't need it. Typically, you don't need it. Regression does that. If you add L2 regularization, it will blend, it will create a mix of L1, that's what's called lasso, L1 plus L2. So in there, it will create a mix of how much should I combine the features that are correlated versus how much should I exclude them. That's for text is a particular problem. Why is that a thing for text? Imagine that you have a lot of correlated features. On one hand, you don't want to include all of them because each one of them will do the job. On the other hand, if there's some words, it takes their words, right? If they're synonym of each other's, it may be that one of the synonyms appears only in test documents. And now if I train and I decided to exclude that because it's very related to the other ones, when I get to a test document, the only description for the concept, whatever's happening in the document, it's with that synonym that I don't have. So there is a little bit of a competition of including L1 selects fewer features. L2 spreads a coefficient exactly like you said. It takes a regression weight and spreads it over all synonyms, all the related features or correlated features. How much you want each one of these effects to happen, it's how much weight you give to these regularizations.
So L1 separates it, L2 kind of.
L1 prevents you to select correlated features. L2 takes whatever weight you have on words that are synonym to each other and spreads the weight on all of them. That's an effect. The mathematics is a little bit more complicated than that. You have to take 6140 to get to this. But yes, that's a thing in particular for text. This problem, it's a well-known thing. Okay, so now that we've done this, my purpose for today is to talk about some of this stuff. So I want to talk about the part in here, mutual information and chi-square. And then I think I'm going to talk about images and leave some of the rest for next week. On mutual information and chi-square, I would like to give you a little bit of background of what those things are. And I don't insist on the math, but I want you guys to know what they are. So the first thing I want to talk about is x is a random variable. Entropy of x is, so when I say x belongs to x, that's not very mathematical. What I mean is x belongs to all possible values of x. X is a random variable. This wouldn't make sense in mathematics. Thankfully, we're not in a math class, so we can write things informally. That is, x, it's all the possible values for the random variable x. So who's the entropy, anybody knows? It's a sum for all the possible values of this random variable of?
Probability of x into log of.
Probability of small x is the value.
Into log of probability.
Log of
Probability of x.
Negative
Negative
right?
signs.
I have to put a minus if I put it this way, or put a 1 over p. That's the entropy. Good. Entropy is a measure of randomness. Low entropy means?
Uniform.
Order.
The other way. Low entropy means not uniform, very skewed. In fact, entropy 0 corresponds to what? To something that's not random. It has always that value. There is one value, probability 100%. The highest entropy is uniform. Uniform variable that has uniform probabilities over the values, like a die. A fair die, 1, 6, 1, 6, 1, 6, 1, 6 over the faces, is the highest entropy with 6. Of course, if I change the 6 to 8 faces, I'm changing the entropy. But for a fixed number of values, highest entropy is with a uniform distribution. Okay? What is, now I have y, another random variable. Of course, I can have h of y, same formula on y. But I want to have conditional entropy. Of y given x. So that's a measure of randomness of y if x is known. In other words, there's one thing to measure the randomness of y. For example, y could be the grades you guys gonna get in machine learning, right? In 6140. Various number of grades has a certain randomness. But X could be the grades you get in data mining. Now, this is a lower randomness than Y, right? If I look at the randomness of Y as part of machine learning grades, it's one thing. But if I say, no, given the grades that are for data mining, now how much randomness is there? In other words, if everybody who gets an A in data mining gets the same grade in machine learning later on, what will be this entropy? 0, because the grade in the data mining immediately dictates the grades in machine learning. Although the actual entropy of Y could be quite high, X predicts Y, so there's no randomness of Y given X, right? So there's a formula for this. You don't have to remember this. Minus somewhere. We'll of course get over this thing. So let's see what happened here. This is writing the entropy out over all. This is the entropy for a particular value of X, weighted with probability of every value of X. Right? So what is this? P of X is here. Now what is the entropy of this? This is for that particular X. Is like the entropy formula, right? Is the entropy of the conditional probability, log of the conditional probability. Hands up, who's with me so far? Okay. What happened from here to here? I move P of X inside, and I use the fact that P of X times P of Y given X. What is this?
P of X given.
This is the joint P of X and Y, right? That's a base theorem that says the joint is 1 times the conditional of the other. So when I move this P of X inside, this times this gave me the probability of the joint. That's the probability of, something and something happening, both of them, right? And what happened here? Same thing, right? In here I had log P of Y given X. By the same formula, I can write that as the joint divided by P of X. Right? Okay. Inside the log. And now this minus comes from? Splitting the log into two things. Okay. So now what is this? This just the first sum.
Entropy of P of X from
X and Y as joint, right? If you look at the formula, this is exactly the entropy formula for the joint. And what is this? It requires a little bit of manipulations, but this is the entropy of x. Because this here could be P of x, right? Average over y. This is going to be P of x, entropy of x, I think.
Plus.
It's minus because the minus in the front.
And then plus.
No, the entropy is minus this.
No, I thought the bracket is open. So
It's, this is, so minus this is the entropy, then minus that is the entropy. So actually, that's the part that you need to remember. As I said, I put here the formulas, because I thought it's nice, but you don't need to remember any of this. You need to remember this. What is this saying? The randomness conditional on x is what? Is the randomness of the joint minus how random x is. So what does it mean for y to be totally dependent on x? This example that I say, everybody gets the same grade in data mining like machine learning. This would be 0, right? The entropy of the joint, the randomness in the joint is the same as the randomness of the first variable. Good. So now that we have this, we can say, what did we just get? Entropy or randomness of y given x is the entropy of x and y minus entropy of x. And then entropy the other way, y or x given y, is the entropy of x given y given x is the same thing, minus the entropy of y. So how should we look at this? There's a conceptual diagram here that says, here's x, here's y. This is actually h of y. This is h of x. This is randomness, how random x is. This is how random y is. And this in here is x given y. And this in here is y given x. And the middle is what? This is the entropy of x given y minus the two conditionals, right? So this is saying this part is the randomness remaining. If this is the joint, this whole thing is the entropy of x and y all together. This part on here is just y without x. This part is x without y. But there's something in the middle which we call mutual information. This I. And you can, whoever's math oriented can prove the following formula. Now that we have a formula for this, and for that, in terms of this sums with probably this, we could derive a formula for y mutual information. And that formula that you have to derive is sum for x in x, y in y, the joint probability times the log of, there's a fraction here, p of x1 divided by p of x times p of y. So if you are so inclined, you could say, okay, how do I take all those formulas? Because I have the formulas for these three, subtract them, do all the derivations, and end up with this formula. Nice. It's in Wikipedia. So what is this? This is saying, if I want to think of this like an entropy sort of thing, it's saying the probability for each, these are like the cells, the slots computing. This sum is over all possible values, right? So this in here is the same as saying x, y have all the possibilities between x times y, right? There's all possible values of x and all possible values of y. Like all grades possible in data mining and all grades possible in machine learning. This is the joint probability of that cell. Every cell in here has this probability, the joint probability. And this is what? Is the ratio between the joint and the marginals, right? You remember the joint probability table? Suppose I have, these are like, I don't know, objects. And this is round. And this is a square. And these are like red objects, blue objects, and green objects, right? These are two random variables. I have a bunch of objects, and in here I can get a count, right? Or if I divide by n, this is the probability of round red objects, and this is the probability of round blue objects, and this is the probability of round green objects, right? So now I could write in this cell, this is the probability of an object being blue and square. That's the count in the cell divided by the total. Because the joint forms the probability overall. So this is saying the ratio between the cell and the marginals. So in here in a cell, you think of P of x and y. That's what I have. But who's P of x? Is the sum of the whole row, right? If x is here, this is probability of, if I sum up those probabilities, that's the probability of round, and this is the probability of square. So if x is round versus square, is this sum is the marginal from the joint on that way, and this sum, these are the two probabilities, round versus square. If I do the same marginals for this is y, what is this going to be? Probability of red, probability of green. For independent variables, what do we know?
Yes.
For independent xy means the probability of xy has to be
What is the product of
You should remember this formula as joint equal the product of marginals. If every cell in this table has the property that this cell is this number times this number, this cell is this number times that number, so on and so forth, it means the joint is the product of the marginals. It means they are independent. But then what will happen in this formula here if the joint is the product of marginals? The log is 0 all the time, right? So there's no mutual information if they are independent. Now, I don't require you guys to remember the math, but some of you are more math oriented. It's a very basic math and problems that you should know. For this class, it's not necessary. But I will require you to know independence and to know not the formula for mutual information, but what it does. It's kind of what's left of randomness. If I look at the randomness of a joint, I can decompose that into 3 parts. How much is randomness of y dependent on x? How much is the randomness of x with knowing y? So how much more random is x after you know y? And the mutual randomness together, which is this part in the middle. That's the mutual information score. And of course, we can plug it in here and say that's our score, right? And we compute correlations that way. All right, so that's good. How about this other one, chi squared? It's not very different. So for chi squared, some people call this this table here, it's a join between two random variables. But if I want to draw the same table between, say I do classification, between prediction, let me write a table. Say prediction versus true labels. Wouldn't I have the same kind of table? You know, here's the true labels, say, you know, class 1, class 2, and class 3. And this is class 1, class 2, and class 3. What would be each cell? This is what? This is the count on how many things got predicted class 1, but in reality the label is class 3. So this is the same table as in that. It's just when we talk about predicted versus labels, we call this a confusion table. So a confusion table, of course the correct values are the counts or the probabilities on the diagonal, right? And the errors are outside the diagonal. Everything that's in here, there, that could be classification errors, right? Because I'm predicting a different label than the true one. But a confusion table is not very different than a join table. Mathematically, they're the same thing. It's just different names. So if I really look at features between features and label correlation, here's what I can do. Again, that's somewhat similar to mutual information. I can say, go further, like in join table. Let's suppose I've got some, let's make it 2 by 2 to make it easier. So I'm going to say true, false, as opposed to true, false. If it's 2 by 2, even the cells have names, right? What's in here?
True positive.
The ones that I predict true, and they are true. True positives. And in here, predict true, but they are false.
Predict true, but
False positives. And in here,
true negative. True negative.
false negatives.
True negative.
Because I predict false, but they are true. And in here,
False negative.
true negatives. Because I predict false and they're false. No?
False negative.
So what's a false negative? False negative. Right?
Correct.
False negative is when I say negative, but it's really positive. Right?
False negative.
So in a 2 by 2 confusion table, those things have names, right? And I can further do the marginals, and I say how many things are here. This is the true positives plus false negatives, right? This is the false positive plus true negatives. And this way are true positives plus false positives. And this way are false negatives plus true negatives. So now, what we want to do is, following this idea here, is to say, I want to ignore the values in the table, the actual values, but kind of do the product of marginals. So in here, I'm going to keep Tn, for example, right? I can divide by n to get the probability. N is the total number of things in the table. What would be the product of the marginals? So Tn is the actual joint probability in this cell. But if I look at the product of the marginals, what is that? It's Fn plus Tn divided by n times Fp plus Tn divided by n. Right? Now if I divide everything by n, let's do another one here. Everything will get divided by n. So these are marginals, those are marginals. In here, what will I have as a product of marginals? Tp plus Fn divided by n times Tp plus Fp divided by n. So in each cell, I kind of have two things. I have the actual joint probability, these, and I have the product of the marginals. Now, if those would be independent variables, they'll be the same thing. So that's what we measure here. He has this chi is this is chi square test. Let's see who this D is here. This is the, I want to take the difference between the value. So it's P of xy minus P of x times P of y squared. So this is the actual value in table. And this is the product of marginals. And this is divided by this P of x times P of y. So this formula could be written as I think I got it right, but let's see. Maybe I didn't get it right. You guys can check the notes later. So this, in terms of the value in the table, for my table here, this is going to be a sum. Let's not write it as a sum. Let's write the cells independently. So this is Tp divided by n. That would be the value in the table, minus Tp plus Fn times Tp plus Fp divided by n squared, right? This thing is squared, and then it's divided by this whole thing, E plus Fn. So the formulas that you might see when you read something is that this whole thing in here, it's called the expected value. Expected means expected independent value. So this might be written as, so plus the other three terms. There's a plus, 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 right? Because I only wrote one of them down. But this might be looking like dp by n minus the expected of dp by n squared divided by the expected of dp by n. Okay, this expected is expected under the independence assumption. Call it AI. So what's up with this test? When is this 0? This is a square value, so to get a 0, each one has to be 0. So it's 0 when the value is the product of the marginals. But when the value is the product of the marginals, that means independence. Right. So this chi square, it says it's 0 when they're independence, and they're higher when they're not independent. Now, I think that's, I don't know how different it is than this. We can try to plot the chi square versus the mutual information to see as function for variables, are they very different or not. But they have the same kind of effect. The higher it is, the more dependent they are. I don't want to insist on the formulas again. I'm not going to ask in this course anything related to those formulas, but I want you to understand how people have thought of these things theoretically. This is a kind of a randomness, what's left after I take x given y and y given x. And this is how each value in the joint here, it's a feature versus the true labels. Right? How each joint value corresponds to the product of the marginals. This is simply an average, right? This D will be the number of cells. This, if it's a confusion matrix, prediction versus labels, it's going to be a square tables, right? Typically, if there's 10, I know there's 10 values for digits, I'm going to predict 10 values, and there's 10 labels. But what about the general feature versus label? Does that have to be a square table? No. I could have a feature that has 3 possibilities, but I could have 20 labels, right? So this is not necessarily square. If it's a feature versus label. So the way it works, I'm computing the expected independence value, that is the marginal product, minus the value, and this gets averaged over the table or the cells in the table, right? That's the principle here. Chi square, you may have heard of this chi square before, and you're certainly going to hear about it again. The formulas, nobody remembers the formula. So if you're worried, oh, I'm not going to remember that, neither your recruiter, the ones who gives the interview, remembers the formula. I mean, if somebody at the interview asks you for a formula, you should say, do you actually know this formula? Because most people, professors, they have to check it out before the class. Unless they work in statistics, they won't remember it. But they do remember how it works, the principle. I've got the independence values, I get the actual values, and take the difference. Okay? So those are 2 scores. There's other scores. If you look for a table, there's some tables. There's like plenty of correlation scores that you can use. And some people very famous for putting up correlation score that works in certain domains. That's what I have here. what this means for you is that you're gonna have to do a bunch of things for homework 3 in terms of feature selections, right? So we're gonna have the same data sets, MNIST, 20 newsgroups, so on and so forth. And we're gonna say, we want 10 features. How can we get 10 features? We can run PCA, like I showed you in class last time, and we get 10 features, or 20 features. Or we can try one of these things, right? We can go by the maximum variance, we can compute chi-squares, we can compute mutual information scores. If we want to use labels, a method that uses labels, but we don't have labels, we can use our k-means labels from the previous homework. Or we can use these farthest far traversals by just computing scores between features themselves and keep selecting features while we see things that are still uncorrelated with everything we have. Now, one more thing about farthest far traversal. If I already have 10 features and I'm selecting the 11th one, I have a score between that one that I'm trying to select and how correlated it is with any one of these 10 features I already have. Should I average this score? Say it's a correlation. Or should I take the mean or the max? Right? So again, the problem is I have scores. Let me draw this down. This FFT idea in graphs. I have already, this is my set of features already selected, right? And I have one feature that I'm trying, maybe 3 features that I'm trying to evaluate which ones to pick. I have between this X, I have correlations with every one of those things. But I need a score for X against the entire set I have. Should I average those? Should I take the mean, the max? What should I do? So the minimum means, let's say in terms of correlation, the least correlated, that's the minimum, right? Minimum is the largest distance. So it makes sense not to average them, because at least theoretically, we could have an X that's far to 9 of them, but very close to 1. If we get the average, that looks like a decent average, but in fact it's extremely correlated with 1 of them, and that makes it not suitable. It's better to pick, so if there is an X that's close to this one, but far from the others, that's not a good feature. But if there's something reasonably far away to all of them, that's probably a better feature that adds something new. This becomes a little difficult depending on the task you have. If you have a certain task, it actually might be useful to select a feature that's correlated to 1 but not to the other 9. But in general, if you don't know what task you have, and here we kind of running blind, right? We don't know what the data is used for. Keeping the minimum, so be as far as possible to everything you have, is probably the right thing. Okay, so what you're gonna have for the homework is a bunch of these trials on the data sets. But then, how do we know we selected good features? Like, any one of these methods would select 10 features for MNIST data set. Then what? We can do clustering, although clustering in itself, unless it's evaluated with true labels, cannot give an immediate notion of whether it's good or not. Or we can rerun homework 1, classification, basic version of classification, right? So if I run KNN, do classification, I'll use not, I'll have to recompute the distance matrix. Why?
The features would actually.
Because I have new features now, right? So the distance, whether it's, I can keep the same distance like Euclidean distance, if that's what I used before, but it'll be a different distance compared to the original distance. So how this process would look like for the homework? I start with the data set X. I have labels, but I don't use the labels. I do say either KNN or K-means. And then I evaluate the output versus the labels. I personally find that evaluations against true labels, it's much more telling than evaluations without labels, but sometimes we don't have any labels, so we use the k-means objective say to see how well did they partition. And then that's what you guys already did, homeworks 1 and 2. But then I do what? I do some feature selection. So there's multiple options for doing feature selection. PCA, K, chi-square, mutual information, and there'll be some other ones. And then I redo KNN. In fact, in here we have an intermediary step, a distance matrix. So I have to do that step again, distance matrix. Then I do the downstream tasks. Those are called downstream tasks. You're going to hear this term that's saying whatever I did had a purpose. I had the purpose of running KNN, so that's my downstream task. That's what I wanted to do with those features. And then I want to evaluate the output versus the labels. Normally, once I do feature reduction, I should get a worse evaluation than before. Like if I do k-means should have worked better here with all the features than would say only 20 features. But sometimes that depends on the actual distance. Sometimes many features confuse the distance matrix. What I want to point out is there's a different way to evaluate things, and a lot of machine learning works that way. Can I do this without the downstream task? Suppose I don't want to do KNN and k-means. Can I evaluate in here? So can I look at my original distance matrix versus the new distance matrix? So call this D, this will be D10 in 10 features, right? PCA explicitly, if you remember the last week, PCA explicitly is trying to match those two things. Remember the objective of PCA? Have the distance between points the same distance like in the new matrix. So I want to preserve the distances between points. Or preserve locations of the point with the previous location. So I could take a look at my distance matrix, that's extra credit, and say, how well this distance align with my new distance? Because these distances are still n by n, right? This matrix still has distances between all pair of points. It's just not computed in in all dimensions. It's computed in 10 dimensions now. But it's still a pairwise distances between all 70,000 images. And in PCA, I should get the closest distance matrix, because PCA is designed to give me the 10 dimensions that do the best job as preserving distances. But preserving distances, while a goal in itself, may not be the best thing for, say, k-means or KNN, right? So in other tasks, I want to preserve ranking, or I want to preserve, I don't know, label distribution, or who knows what. But I could, in principle, evaluate the distance matrix. So for the ones of you who want to look further into this, you should observe that when you do PCA, you get closer distances to original than when you do the other crazy stuff. Especially if you run PCA with, say, 20 dimensions or something larger. Like I think I showed you, I ran PCA with 20 dimensions, and the downstream tasks worked almost identical with 784 dimensions. When would distances be the same in PCA? When would I get the same distances with 10 dimensions, like I get with full? When? So what would be necessary so that when I ask for the top 10 PCA features, I get the same distance matrix like the original? No information loss, which means?
More variance for the one.
There are only 10 eigenvalues which are non-zero. The other eigenvalues are zero. So if I have out 784 eigenvalues, I get only 10 non-zero, and the rest of them are zero. It means my data really lives, or even though it's a 784 dimensional space, my data really lives in 10 dimensions, right? And then PCA rotates those so that the 10 dimensions that are the data dimensions align with the top first dimensions. And you say, give me the top 10, the other ones are 0 anyway. So the distance now fits exactly with the true distance. Again, if you want to study this more, you can do these experiments with PCA. PCA has the advantage for you guys on laptops that's actually in MATLAB. It's very fast. You can run it on a laptop. Some of these other methods, you need a workstation or a server to run it. Even for toyish data, so like 70,000 things, you won't be able to run some of this stuff with all images on a laptop. But PCA you can. Question?
So when you're measuring the correlation between two distance metrics, right? When you say about the distance between these two, you're telling the relative distance in those.
So in this matrix, I have distance between any I and j.
Okay.
Right? It's a distance Euclidean, if I was Euclidean, or cosine, or Jaccard coefficient, or Minkowski distance, or whatever distance between image I and image j. Right? So there's 70,000 choose two distances in there. What I'm saying is that it's possible that the distances, even computed only 10 dimensions, are the same distances like before. That means my data had a very low rank, right? A lot of the eigenvalues were 0. Okay. By the way, this cannot happen for text. Text, due to the sparsity nature of text, it's impossible to have all data in only 10 dimensions. There's no 10 words or 10 concepts that will be good for 18,000 documents. So this typically applies to images or some objects that have this dense representation.
But what if there are common words across 18,000?
The common words usually have no information. The word "the" appears in all the documents, but it's also completely useless.
Right.
So there's no way to find common words that are very meaningful in all the documents. No meaningful word or rare word like Virgil will be in more than 0.01% of the documents.
Right. So now the common word, we can completely eliminate that dimension, right?
Common words you can completely eliminate for the purpose of classification or anything useful. Now as a representation, even as representation, every document tends to have the same proportion of "thes" in it. It's everyone in 7 words in English is a "the." So as a proportion, typically all documents have the same feature value for that word. Most text languages and natural language processing pipeline eliminates those so-called common or stop words. Okay. The other thing that we need to do today is to talk a little bit about the hard images. I'm going to split your homework tree into 2 parts, all these feature selection mechanisms. So next time I'm going to talk a little bit about classification, but you won't need regression and decision trees to implement them. You'll need just to run a package. So I want to talk about, I don't know what number that was, image features. The alternative is what? Anybody knows how to extract features from images in practice? How do people do it? If I want to classify image, very simple task, right? I could do 784. Those are raw features, right? It's actually pixel values, right? That works extremely poorly in practice. I mean, MNIST data set is one of the few data sets for which this actually works in practice. Imagine you have real images, 3,000 by 2,000, right? How many pixels are there? 6 what? Million, right? Imagine if I use 6 million pixels to do face recognition, you never recognize anything, right? So what do? I'm Facebook now. I have images, lots of them, right? I don't want to use pixels, so what do? For text, people use unigrams, and unigrams, words, are quite successful. The challenge there is engineering. You have to use a sparse format at all times. Anything with text requires sparse formats. You cannot use a dense format because things blow out. But using unigrams in a sparse format has been showing quite consistently it's good for a lot of tasks. Some people use bigrams, right? They want to use virtual Pavlov, that's fine. But for images, this is a real problem. Extracting features from images has been a challenge and is still a challenge. And sometimes we ask people to label features for us. Like, is there a tiger in this image? And people label yes, no, yes, no, yes, no, right? Tiger or no tiger. That becomes a feature, right? Because if I label all my images on Facebook, tiger or no tiger, I got a feature called tiger. Is there a tiger or is no tiger? Did you ever label images?
Capture.
You did, all of you. Every time you set up a CAPTCHA, somebody's asking you to label something in images like stop signs, storefronts. Is there a person and a car in this image? And you said yes because you want to move forward, right? You just label a feature for an image right there. Right? Why is this difficult? We don't want to use pixels, and there's no obvious way to transform pixels into reasonable set of images. So other than these hard features that are some sort of heuristic people came up with, they show that work sometimes with certain downstream tasks. They don't do it all the time, but with some algorithms they do. Anybody knows how grand companies like Facebook do feature extraction for images?
CNN.
What that stands for?
Convolutional neural network.
Correct. So the alternative is CNN. Or recurrent neural networks, some version of neural networks. That's what's being used today. If you want a job in feature extraction for images, you cannot avoid neural networks, CNN, RNS. That's the standard today for feature extraction from images. We'll do that maybe after the spring break. Let's see how complicated it really is. We use TensorFlow to do so. But before, I can give you some much more down-to-earth mechanism that you're going to understand what it is. This is complex because it requires a large infrastructure, neural networks. And the mathematics behind it is very complicated. You're going to get features. You say, I want t equal 20 features. They're going to give you 20 features. There'll be no way to interpret those features. There will be a completely mystic feature values that do the job, but you have no idea what they are. These hard features make a lot more sense what they are. So you can actually debug your algorithm to say, okay, what happened here? So here's how people have thought of these hard features. This is my image. And I want to cut a rectangle in it. And so I have a rectangle of, say, it has coordinates, right? So it has x1, y1, x2, y2. The first thing is, I want to get this rectangle across all images. Easier to say than to actually do it, because that makes sense if all images have the same size, right? Like in MNIST, it's 28 by 28. If I define a rectangle, I can take that rectangle across all images. What if I have various sizes? Then what? Maybe these are proportions now, right? So this x, y, it's 20% x, 50% y, 35% x, 45% y. And now in every image I can go to 25%, 35%, right? So I want this to get this rectangle and some consistent notion across images. If you think of images as a stack from the board, this rectangle crosses to all images, for all images, gets you a rectangle. Now I want some sort of value in rectangle. I can compute all kinds of things. For example, average exposure, or average number of white pixels, average proportion of white pixels. can compute values in rectangles. What else? Contrast. All kinds of other things. And I can compute values as deltas. Between rectangle left versus rectangle right. So what I mean, I take my rectangle, I cut it in half. That rectangle. This is the rectangle left side, this is the rectangle right side. And now I can say delta could be, there's also a bunch of things, you know. How much color is on the left versus on the right. Like the delta, this is delta in color, delta in contrast, delta in brightness or exposure. By the way, exposure is not the same as brightness. I know that. Don't criticize me if I know exposure is not the same as brightness. But in here, it's any statistic that you can think about this rectangle, right? Exposure or brightness. For simple images like MNIST, I can just compute how many black pixels I have on this side versus this side, right? Now some rectangles would have 0 deltas because they have all white and all white, so there's no deltas in between. And I can also take values as delta between top versus bottom. So I can take my rectangle, split it this way, and have rectangle top versus rectangle bottom. Rectangle left versus rectangle right. I can do the same. So for every rectangle, I could get few values purely as a function of the rectangle, few values as delta left versus right, and few values as delta as top versus the bottom. This is usually exactly in the middle to not complicate things. So say total, I get for a rectangle like this, I get say k values, k above 10. Because I get few of these. Depending, I have to know a little bit of the images. You know how much variations in the color you can add that. Delta variation in color gamut or variation in dominant color. So I get a bunch of features for a rectangle. Now I could cut a different rectangle. I could say here's another rectangle. That's my rectangle 2. Or I could cut a different rectangle. That's my rectangle 3. Cut a different rectangle. That's my rectangle 4. So I could cut different rectangles. For each rectangle, I'll have that many features, right? So now if I have T rectangles, this has to go through all images. Will result in total in how many features? T times K, which is total. In some sense, for people who know convolutional neural networks, that's the basic idea anyway. Convolutional neural networks look at chunks of the image and compares it with other chunks and decide that that chunk, aka a rectangle, it's useful. Now it does it not in a heuristic way, but that's where the idea comes from. Now, assuming I don't want to go into image composition and how exposure versus contrast versus other things work, but how do I do this? How many rectangles are in an image that's, say, 2,000 pixels by 2,000 pixels? How many possible rectangles are there?
Depends on the size of the.
If I say a pixel is 2,000 by 2,000, all pictures are the same size. They have been normalized, say, same size. How many possible rectangles, unique rectangles, are in this picture? Hmm? So you know what I mean by possible rectangles? I just show you 4. I could draw a lot more rectangles. So how many different rectangles are in this frame, 2000 by 2000? No. It's combinatorics 101. So is it true that anywhere I pick 2 points, this is my image, any 2 points dictate a rectangle? A unique rectangle? Is that true or not? Is it? So those 2 points, what rectangle they dictate? How do you determine the rectangle given 2 points? Does have to be the diagonal, right?
Yes.
So this rectangle is this one. Isn't this the same rectangle as those 2 points? So every pair of 2 points dictates a rectangle that's not unique. It's also dictated by another pair of 2 points. So how many pairs of points I have? How many total points I have here? Pixels is 4 million. So how many pairs of points do I have? As I say, every pair of points dictates a rectangle, but every rectangle is counted twice. It's counted once for this pair and once for this pair, right? If I say every 2 points dictate a rectangle, I'm about right, except I count all rectangles twice for every diagonal. A rectangle has 2 diagonals, right?
Yes.
Some of you are stunned. Why is that? We know about rectangles, right? Why are we so stunned? So how many pairs of points are there? 4 million. Choose 2 pairs. But every rectangle is counted twice. So the number of rectangles is? Even divided by 2, 4 million choose 2 is a very big number. Right, and if I have the same line, I have one rectangle, then maybe it's counted only once. I could still measure that whatever luminosity or contrast or difference, perhaps, it will make some sense to look at just that line. There'll be very few pairs that are on the same line, right? The chance of getting the same line is about 1 in 2,000. So I could exclude those if I want. My point is this is a big number. We don't want to go around and play with 4 million choose 2 things. So, of course, the numbers I pick, let's say the number of rectangles you guys going to extract from features from MNIST data will be about 100. We don't need more than 100 rectangles. Times, if each rectangle produces few features, in MNIST you won't get 10 because there's no colors, there's nothing. You'll get like 3 or 4 features for rectangles max. So you'll end up with 100 rectangles times 3 or 4 features, 300 features. Those 300 features will do classification even better than the pixels themselves if you select the right rectangles. The question is, how do I actually compute all those statistics? So I'm going back to my image here. Suppose I want to measure something that's quantitative, like the number of black pixels. I want to get the number of black pixels. How do I measure in an image? I have a rectangle. I want the number of black pixels. That's one of my hard features for a rectangle for MNIST data set. I could go in this rectangle and count how many black pixels are, right? That's a very inefficient of doing it. The efficient way of doing it is to think of this rectangle as what? This is A, my rectangle is A, B, C, D. I put here O, I put here say M, N, and P, and Q. Number of black pixels in rectangle A, B, C, D is what? Is the number of black pixels in O, N, C, P, right? I'm counting all of them. minus, now I want to take out this thing, OQDN. So I took out this part. Now I'm going to take out this part, which is the number of black pixels in OPBM. But now I have a problem. I took this rectangle out twice, right? So I have to add it back. Number of black pixels in OQ. Why is this easier? Why doing it this way it's easier than counting the black pixels? All these rectangles have a property. All the 4 rectangles here have a property. They have the top left corner in all. So the right way to do this is in 2 phases. Phase 1, compute my statistic black pixels for all rectangles starting in this corner. There's not so many. How many rectangles start in this corner? Only 4 million. 4 million is a lot better than 4 million squared. Right? So I can compute in here all the, because every rectangle for every point, I get a rectangle with this corner. And then every other rectangle statistics can be obtained by taking the statistics of 3 or 4 rectangles that I already have from phase 1 with the corner in O and making the difference. Okay, more feature selection next time.
这作业感觉越来越。
他说的什么？他说要有一次大作业。
对，然后 spring break 那个什么意思啊？就是 spring break